So just a few announcements for today. So from last time, we talked about the homework and the CFD project being due, and I've moved those back to next Thursday at 11:59, so basically the last possible moment before your reading day begins. Now, this does get pretty close to your exam, right? Remember, the final exam is on Monday, right, the 12th. So I do encourage you to, to get going on this sooner rather than later, because it is going to get a little bunchy there. But I know you have other stuff due, and so so I have pushed the due dates back to Thursday instead of Wednesday. So just note that that's a change from our normal kind of pattern. Another thing, it's course feedback time. Course feedback is open. I very much pay attention to this. So for example, from past feedback, just some examples, we now cover CFD. That was a big request the first time I taught the class. The lectures are recorded. That was another request. I put examples on YouTube. That was another request that came through course feedback. And there are others as well, other changes that I've made, some big changes to the class based on your feedback. So I really do value it. And to reflect that, I'd like high response rate. And so if we get to 85% response rate before the final exam, then I'll send out 2 hints to the class. And I've done this in the past. And they, they'll tell you like something specific that you should study, or something about the structure of the questions. But I will give 2 hints if we hit 85% response rate. I think I checked yesterday and we were at like 3%. I think there were just 1 or 2 people who had filled it out. Once we get to 85%, I'll send out 2 hints. We don't have as long as in years past, right? Because the final exam is on the first day of finals. Please fill out the feedback. Encourage your classmates to fill out feedback. I do pay attention. All right, any questions on assignments or anything before we get started for today? Just speak up. I can see some of you in the video, and I'm kind of scrolling through as I talk. Just unmute and speak up if you have any questions. Okay. All right. Okay, so today we have just a few things to finish up in chapter 9. And we're going to do that actually first. And then there are some videos explaining compressible flow concepts that I want to go over. I hope they land on Zoom, so we'll see how that goes. But including, we kind of talked through what happens when you have a converging diverging nozzle and we decrease the back pressure, right? We talked through like shocks that form and how they kind of move through the system, but we have, among other things, a video explaining that. We've also been looking at some flow visualizations in compressible flow all throughout this chapter. We're going to look at a little bit more about how that kind of thing works, just so, and I think it's a nice visual explanation of how that works, just so you can understand the videos and things that we've been looking at, and the images that we've been looking at all through this chapter. And then where we're going, we're almost done here. Monday, we're going to go over how does an airplane fly, basically by reviewing concepts from the semester. So we'll see that we can understand how an airplane flies using Bernoulli, right? So basically an energy balance. Also by understanding momentum and doing a momentum balance, we can understand how an airplane flies, and we'll tie that into the concepts that we've done from the semester. So it's sort of like a review of some of the concepts that we've done, that we've covered, applied to flight, because I do think you should be able to understand how an airplane flies by the time you get to the end of a fluids class. I will note, and we'll cover this on Monday again. I think your TA was a little bit misleading in his lecture when he talked about equal transit time, that air takes the same amount of time to go over the top of a wing than the bottom of the wing. He said something like that, and that is not true. But we'll talk about that in a little bit more detail on Monday. On Wednesday, we're going to have our final exam topic review. This will be pretty much the same idea as what we've done for the midterms, but now applied to topics on the final. One thing to note there is that the final is cumulative. So that in that topic review, typically in 50 minutes, we only have time to get through a couple material from topics from a couple of chapters. So we're going to focus on the new stuff in that final exam topic review, but I will refer you to the midterm topic summaries that we did before midterm 1 and 2 as other material that could also be covered on the final. So we'll try to hit the high points on Wednesday, but of the stuff from midterms 1 and 2. But yeah, I just wanted to make you aware of that. We're going to focus in that topic review. We're going to focus on the newer stuff. Okay, so before we get back into it, any questions? Okay, great. So one of the worst things about Zoom is that I can't see you, but luckily many of you have turned your cameras on. Thank you very much. But one of the other worst things about Zoom that I'm hoping we can fight against is the lack of feedback, as in nobody ever says anything. So I think one of the best things about being in person, and one thing that I've noted about your class in particular, is that you're very interactive. You ask a lot of good questions, and I like that. That makes for, I think, a more enjoyable class period for me from here. Also, I think it prompts us into some discussion that is hopefully useful for you all. So I encourage you to buck that trend and ask questions, even though we're on Zoom. Okay. All right. We're gonna get moving. So just as a reminder of where we came from, because we kind of went over this a little bit fast on Wednesday. We've been talking about compressible flow, and we basically developed two ways of addressing problems in compressible flow. The first is for isentropic flow, right? So we developed isentropic flow relationships, and we use those to look at what happens for compressible flow, like through a duct, through some internal region where we have a change in area, right? And then the second approach that we developed was for when we have a shock wave that forms. And we said one of the ways that we can have shock waves form, one of the places that we can have shock waves form is inside of a duct of changing area, and we can have a shock wave form. And then we have the shock wave equations that we developed, where essentially everything is a function of the Mach number upstream. And one way that we can put this together, and that you're seeing on your homework, that we can put this together, is if we have a duct of known shape, and we have known, for example, stagnation conditions upstream, or known conditions somewhere within this shape, we can use isentropic flow relationships in some regions. So for example, here from stagnation through the throat all the way up to this condition 1, which is the stagnation side of this shock, the left side of this shock. Can you all see my cursor? I just want to check. Yeah, okay, cool, thank you. So on the stagnation side of the shock, we can see we can use isentropic flow all the way from stagnation up until this side of the shock, right? Because this is isentropic on this side. Across the shock, the flow is not isentropic, right? We have an increase in entropy, right? Because this is thermodynamically irreversible process. This is we're losing a lot of this is a kind of violent process. We're losing a lot of energy, and so entropy is going up across the shock. And then on the other side of the shock, to get from say position 2 to position 3, we would use isentropic flow tables. So if we're dealing with air, so we have tabulated values of the isentropic flow relations and the Mach number relations for shocks, the normal shock relations. And these are given in table B1, which we showed previously for isentropic flow. And then normal shock relations are shown in table B2, right? And so this shows, for example, as a function of upstream Mach number, so this would be like Mach number here at section 1, is what's shown here. We can see, what is the downstream Mach number? So the Mach number just immediately on the other side of the shock. What is the ratio of pressures? What is the ratio of velocities or densities? And what's the ratio of temperatures? Stagnation pressures, and that critical area at which the shock would become, at which the flow would become sonic or choked. So you're gonna have a chance to work with this on your homework. And if you haven't already, I'll try asking your question. Why is this, if you look here on the left-hand column, it's all greater than 1. Why is it all greater than 1? Just unmute.
Because it needs to be supersonic for there to be a shockwave in the first place.
That's exactly it. For there to be a shockwave, it needs to be supersonic. And so the flow, so the Mach number upstream, which is what is in this left-hand column, that needs to be greater than 1, right, in order for us to have this shockwave. And when we have a normal shock, so this case of having a shock that is 90 degrees perpendicular to the flow, then the Mach number on the other side of the shock is less than 1, because we always go in a normal shock, we always go from supersonic to subsonic. Now your text does talk about oblique shock, so that would be a shock at like an angle to the flow. And when you have an oblique shock, it's possible to have supersonic flow downstream, but that's not a case that we're going to be discussing in this class. Okay. One other thing to note is that, and we'll see examples of this in videos, and we'll hit on this again when we're talking about it in the videos. But a normal shock wave can occur within a duct, so it can occur in internal flow. It can also occur in external flow. So if we want to understand flow across a shock wave that is just immediately out in front of like a blunt object, we'll see some images and videos of this. We could actually use the normal shock relations, at least for the part where the shock wave, again, is perpendicular to the flow. But we'll see that in videos in a few minutes. Okay, so yeah, so from 0 to 1, isentropic, 1 to 2, normal shock, and then 2 to 3, we would go isentropic. Isentropic, though, with new stagnation conditions, new A star. So just some notes on normal shock waves. So upstream flow is supersonic, downstream flow is subsonic, just as we said. This is another example. So here on the right-hand side of a shock wave, right? So this is a cylinder at Mach number about 1.5. And we can see that, you know, there's a curvature to this. We're actually talk about the angle of that curvature in a few minutes. But the normal shock relations would still apply here. You see where my cursor is, right along the center line of that cylinder, where the flow is normal or perpendicular, right? Just at this point where the flow is normal or perpendicular to the shock wave itself. So the normal shock relations don't apply once we get out here and we have this kind of angle, right? Relative to the flow. We call those oblique shocks. And again, we're not going to talk about like what happens across an oblique shock, but right here, we can say something based on those normal shock tables. Okay, so we can use them both for internal and for external flow. So you know, one thing to note that with few exceptions, pressure must increase downstream of the shock wave. This basically has to do with the idea of the specific heat ratio as being greater than 1. Your textbook claims that there are some exceptions to this, but I can't find any where the specific heat ratio is less than 1. You know, for all intents and purposes, pressure must increase downstream of the shock wave when we have a normal shock. Again, entropy increases across a shock, so therefore we have a decrease in stagnation pressure, a decrease in stagnation density, and an increase in the effective sonic throat area. So A star goes up, P naught and rho naught go down as we move across the shock wave. So our stagnation temperature stays the same, but our stagnation pressure and our stagnation density change across the shock. Weak shock waves are very nearly isentropic, so there's really not much difference in these things across a weak shock wave. If we go back, we can see that as we, for example, increase in Mach number, as we increase in Mach number, we're getting stronger and stronger shocks. And therefore, if we look here at the stagnation pressures, we can see that stagnation pressures for a shock at Mach 1.1 is a very weak shock, and stagnation pressures are basically the same, 0.9989 ratio across the shock. But as we get to stronger shock waves, we see there's more entropy increase, right, across that shock. There's more increase in disorder across the shock. And therefore, there's a bigger change in the stagnation pressures. Shock waves can occur in both internal and external flow, right? So we've been looking at visualizations of both, and this normal shock relation, again, we could use an internal flow or an external flow in the region where the flow is perpendicular to the shock wave. Okay, just scrolling through the videos, making sure everybody, it looks like they're on the same page. Okay, so that's what we're going to say about normal shocks. Again, any questions on that before we move on? We're going to talk about the angle at which shocks can occur, but okay. And this is a concept of Mach waves. So if we have, let's consider some object that's moving through a fluid, say it's air, and we'll see that if the object is moving and it's subsonic, right? If it's traveling at a subsonic velocity, then any kind of pressure disturbance, any kind of noise that the object is making, right? Noise is a pressure disturbance. Those pressure disturbances will be traveling outwards from the object at the speed of sound, right? So that's what the speed of sound is. It's the speed at which pressure disturbances or sound travel outwards from an object. And if we're subsonic, then those pressure disturbances are traveling faster than the object itself, right? So that's shown here schematically as, like, imagine this object moving from this little point here to this little point here over some time delta t, and it's emanating sound waves, right? You can think of this as like the the engine noise or something, or just literally the pressure disturbances that it's making to the air as it travels through it. And those are emanating outwards in these kind of circular things that are increasing in size at the speed of sound, right? So imagine these are like ripples in a pond moving away from the object, right? These are like sound waves moving away from the object, and they travel at the speed of sound. And when the object is traveling at less than the speed of sound, right? So subsonic, Mach number less than 1, those waves, those pressure disturbances, those sound waves are moving faster than the object itself. They're moving away from it faster than the object is. But when we reach the sonic condition, when we achieve this Mach number of 1, then we can see that the object here is traveling exactly as fast as sound is moving away from the object. And so, every time one of these waves is launched, right, like a sound wave is launched from the object immediately, is catching up with it, is keeping up with all of those sound waves as it moves through the medium. And so they start to pile up, right? And that's kind of what's shown schematically here, is that, as the object is moving through the medium, all of those sound waves are kind of piling up in front of it. And then as Mach number gets greater than 1, right? So as the object now starts traveling at a velocity that's faster than the speed of sound, and now, imagine this is the, so shown schematically, if this is where the object was at time t0, this is the sound wave that was launched at time t0 after some time delta t. But in that time delta t, the object is traveling faster than the speed of sound, and it's now moved even further downstream than this sound wave has traveled, right? So it's now outrunning the speed of sound, right? The object is traveling faster than the speed of sound. It's outrunning all of those pressure disturbances that it's made. And so instead of creating this, instead of having all the waves just like pile up on top of one another, we'll see that those that we end up with kind of like a cone shape of the pressure disturbance, right? A cone shape of the noise that was generated by the object. And what this will look like, or how you would experience this is, first of all, you'd see this this cone is actually visible as a supersonic Mach wave, and we'll see it as a shock wave typically. So we'll see a shock wave that has this like cone shape to it. And if you're upstream of that shock wave, so if you're standing on the ground, underneath this this object passing by you, right? So you're standing right here, you can actually look up and see the object passing above you, right? So if there's like a supersonic jet going above you, you'd see it pass above you, right? Directly overhead, and then you wouldn't hear it until the point where this cone sweeps past you on the ground, right? So so out here, it would be silent. The object is traveling too fast for the sound waves to have reached you yet. And then once you cross the shockwave, you'd hear a sonic boom. And then inside of that, and then beyond that, you'd hear like the engine noise and everything else coming from the airplane flying overhead. So this creates a cone shape. Outside of this cone, you can't hear the object, as we said. And we can actually then find the angle of this cone really just based on geometry. So if we know how fast the object is going relative to the speed of sound, like what U over A is, right? Because that's our Mach number, is U over A. And just by doing some geometry, which we won't go into here, but the end result is that the angle of this cone is the inverse sine of 1 over Mach number. So from the Mach number, if we know how fast the object is going, then we can figure out the angle of this cone, or vice versa. If we know the angle of this cone, then we can figure out the Mach number. So there's a problem on your homework that you didn't have the tools to solve on Wednesday, but you now do, where you're going to be asked something about this, okay, about angles. And there's another problem actually that I almost gave you on your homework that asks, like, if you're standing on the ground here, how long, and you can time how long it takes for the supersonic Mach wave to come past you. You can actually then figure out how fast the object is moving from that. And again, we're going to see an example of this in a video where we'll look at a supersonic baseball, and from looking at the angle of the Mach wave, this will be from Smarter Every Day, Justin from Smarter Every Day, very enthusiastic experimentalist. He'll show us how we can he'll actually use this relationship in order to find the speed, the Mach number of the supersonic baseball. So again, we'll see that in an example in video, but we can use this if we have a photo of an object that's traveling faster than the speed of sound, where we can see the shock wave. We can actually measure the angle from this photo. And so this is a photo of a NASA T-38 aircraft. This is done with this really cool Schlieren technique that actually works when the object is flying, which is cool. Schlieren is a technique that we're going to look at in video in just a second. It's a way of visualizing density differences in the fluid. And this is now of an entire actual full-scale airplane as it's actually flying, which I think is really cool. And from this, we can actually measure the angle from this photo. So I just went in and measured the angle, right? Got out a protractor or something, measured the angle. And from that, we can tell how fast the plane is flying, right? There's a little bit like that Taylor bomb analysis, but definitely not, the military definitely knows, NASA definitely knows that we know how to do this. This is basic compressible flow stuff. But we can figure out the speed of this plane. And so we get that the sine of this angle, hold on, we can figure out the angle. Yeah, sorry for the disturbance. And from that, we can figure out that the Mach number the Mach number of this plane is about 1.1, right? So we can tell, how fast, or at least what the Mach number was. Yeah, so the question is it in degrees or radians? Was a question from you. I mean, it's I guess your calculator can do it either way, right? With numbers in degrees or radians. Here, this was I measured it in degrees, and then I set my calculator to take sine in degrees. So just make sure you're consistent when you're doing that. Does that answer your question, Francisco? Yeah. Okay. So from this, what we'd see is that a larger Mach number will have a say shallower angle. I really mean that like the cone will become more, we'll have like a sharper point to it as we end up with a larger Mach number. So here, this is an image of a again a cylinder at Mach number of 4, and we can see that this cone trails off at or would come together at an even steeper point. And here we have Mach number of 8.8, and we can see this even the cone coming to an even sharper point as we get to even higher Mach number. And again, we'll see an example of how we can use this to actually find the speed of a supersonic baseball and determine it was launched at 1,000 miles an hour.
Professor?
Question.
Is the shockwave angle irrespective of shape of the object, or do we have like a pointed object? Is that going to change it?
Yeah, good question. So the question is the shockwave angle irrespective of the shape of the object? And to some extent, yes. Okay, when we get far away from it, and you can kind of see that here. So when we have a sharp point, like here we have this kind of like fairing at the front of the plane, or here we have an object that is really just a sharp point. Then we can see that the shockwave angle starts from that point, right? The Mach number angle starts. Okay, sorry. Yeah, no daycare means kids running around making noise. So yeah, go ahead.
Well, we just love them. Also, why are there multiple shock waves coming off of each? They look
Okay,
like
let's start with the shape thing, because we didn't really finish that there. So you can see that when we have a blunt shape, we actually end up with a normal shock in front of it, right? You can see that normal shock in front of it, and then it kind of curves around. But the angle that we're talking about here for this Mach cone would be the angle of, imagine if we take these shock waves that are behind and they kind of come out and meet at a point in the front. So that angle would be this Mach cone angle, okay? Whereas when we have a pointy object, we end up with that shock wave basically attached to that point, and the angle comes back like this. So the reason why there are other shocks downstream. So remember I said something that we're not going to cover how to analyze in this class is that when we have an oblique shock, so we have a shock at some angle to the flow, right? Like this shock wave here, or like the shock wave out here away from this normal shock region, right? In front of this blunt object. Then the flow downstream can still be supersonic. And so that's what we're seeing here. So the flow downstream is still supersonic. And so, right, because this is not a normal shock. So for a normal shock, the flow downstream is always subsonic. But when we have an oblique shock, the flow downstream is not, can still be supersonic. And so therefore, when this flow downstream that's still supersonic encounters another disturbance, right, on the body of this airplane, then it launches other shock waves. That makes sense? It's a little bit of a confusing concept. So that's one thing that's happening here, is that we're seeing that even though we have a shock wave here, this is not a normal shock. The flow downstream is still supersonic, and so when it encounters other disturbances, other things on the airplane, it can launch new shock waves. Another thing that's happening here, if you look, these angles are not all exactly the same. And as the flow is moving over the airplane, it's changing velocity a little bit. And so we're actually accelerating or decelerating as we move over the object. And so the Mach number at which each of these disturbances happens actually changes a little bit as we move downstream. Okay. Any other, does that answer your questions though? All right, I don't hear anything, so I'm going to assume yes. From the thumbnail videos, I can't quite see what's going on in the lecture hall. Okay, just as a note, we've barely scratched the surface here, of what can happen in compressible flow. So much more complex shock and expansion wave patterns are possible. So this is another image of some airplanes in flight showing the shock waves that are forming around them. And we can see here, so these planes are flying at just over Mach 1, because this is a relatively flat Mach cone, right? So we can tell that now. We can see there's a normal shock right here. Spreading out into this relatively flat Mach cone. But then there are these much more complex shock and expansion wave patterns that are happening downstream. And those are beyond the scope of what we're going to cover in this class. But these are essentially launched by the other disturbances that are on the or occurring as the flow goes around the airplane body. And these things are, shock waves are waves, and they can interact with one another. And we can see some of that here, right, where we see the bow shock. Okay. And we can see those waves. We might have a special visitor in just a second. My son wants to see what I'm talking about. And so we have these other more complex interactions as well. And when these interact with each other, they can give rise to very complicated interactions. Like these are shock waves that are now forming in the expansion from a jet, right? And that's another example of this kind of thing. Okay, so we have some videos that I wanted to share with you all to kind of explain some concepts in supersonic flow. I just realized that I'm not sure that my sound is going to come through on Zoom though. Let's see if I can figure out how to make that work. All right, we might have to go to my speakers on my computer, and we'll see if you can hear the sound coming out from the YouTube videos. Okay, if not, I guess we're going to watch them without sound, and I'll talk you through what it is that we're looking at. Let's see how we can do on this. Yeah, so now we're all going to watch these videos. Sure, Eli. Okay, this is my son, one of them, and he wants to watch videos with us as well. He's pretty excited about this. All right, so we're going to try. I'm going to switch this to the MacBook Pro. Apologies for background noise, but now you're going to be able to hear everything. Hopefully, you can still hear me. Can I get a thumbs up if you can hear me? Okay, cool. The speaker is going to be the MacBook Pro speakers. Okay, and so this first video is going to be an example of the Schlieren technique that we've been talking about. Let me just sit down. And we're going to see. So this again is a technique that we've been looking at images from really throughout this chapter. It's a way of visualizing differences in density. And one of the classic ways that we can see this is if we have like a hot candle or something, it can cause changes in density.
Wow.
Okay, hold on. I see a lot of chat going on. Okay. Got it. Okay, so can you hear the video at all? No, doesn't sound like it. Let me try one more thing and see if you can hear the video now.
You can see that because as the reflected light from the LED passes through this column of hot air, it changes directions ever so slightly. That is, it refracts. And the reason for that is because the refractive index of hot air is different from the refractive index of the cooler air around it. Now, refractive index is a measure of how fast light travels through a medium relative to its speed in a vacuum. So for air, the value is pretty close to 1, but hotter air actually has a lower index of refraction. In this case, the difference in refractive index is incredibly tiny, and so we don't notice the deflection of the light. But with this setup, it actually makes a difference because some of the light that would have passed over this razor blade instead gets deflected down and gets blocked. And that forms a darker spot on the image. Similarly, some light that would have hit the razor blade is instead deflected over it, creating a brighter spot on the image. And that is how this works. So you can see the heat rising off your head. And you can see your breath. And you can see the cold air poured out of a cup of ice. But temperature is not the only thing that affects the refractive index. Different materials, different substances, they have different refractive indices. For example, the butane in a lighter, obviously we can't see that it's coming out right now, but the camera can, even before the lighter is lit.
James. What? That one.
Okay. So we've been using this, or we've been looking at visualizations using this technique in order to see compressible flow, right? So in compressible flow, we've learned that when we have a shock wave, for example, in a normal shock wave, there's a large difference in density, right, across that shock, right? So here we can see this is the difference in density that occurs across the shock wave. And that difference in density as we move across the shock causes a difference in refractive index of the material, which we can then visualize with this technique called Schlieren. And so all of these images that we've been seeing like this are essentially Schlieren images that allow us to visualize differences in density and then see and see the shock waves. These are shock waves that are characteristic of compressible supersonic flow. So I encourage you to watch the rest of the video. This is a fairly long video. We're not gonna have time to go through all of it for more details on the setup and how it works. But we got kind of a flavor of that in this little segment of the video, showing how, where Derek from Veritasium is talking about how there's a light source positioned next to a camera, a big old mirror that's right next to the object. And then we block out some of the light that's reaching the camera with this razor blade. And using this setup, we can actually then visualize the differences in density. We can do this in color as well. So if instead of using a razor blade, you put filters of different colors.
By blowing a bubble with the rainbow Schlieren.
Then we're actually gonna be able to see this in color. So let's give this a second here.
Wow. Funny. I didn't do that.
Another crazy idea of yours was to light a ping pong ball on fire because ping pong balls, the good ones anyway, that they use in actual tournaments are quite flammable. So I'm going to see how that looks. Whoa, it's caught fire.
Okay, so we could probably spend the entire rest of the class period, the next 10 minutes watching just this thing in color. But again, I encourage you to look at this video for just another demonstration. So in this case, instead of having a razor blade, so we end up with a black and white image, there's actually a color filter in front of the camera that does much the same thing. Just as encouragement, of something that you can do in your senior capstone project. So I had a senior capstone team actually try to build a Schlieren for me a couple of years ago, maybe 2 years ago now. What they ended up building was actually a shadow graph, which is kind of related technique that can also allow you to visualize changes in density within a fluid. And so this is a video that was taken actually with my phone on the device that those students built. And you can see the density difference in the air above a candle that we could actually see with this thing that we built. That I was going to try to set up in front of the room for you all today, but wasn't able to. I know some students in my class actually did. And then, so with that technique, we can visualize differences in density that are caused by shock waves, again, characteristic of supersonic compressible flow. So we can use this to understand what's going on or visualize what's going on in supersonic compressible flow as well. So in this, so we'll look at now applications of that to both internal and external flow. And so this is again, one of these NSF films on fluid mechanics, where we can see, in this case, flow through a converging diverging nozzle, which we've been talking about. Hold on, give me, where we can see flow through a converging diverging nozzle, right? Which we've been talking about. And down below, we're actually visualizing pressure. This is like we have, essentially manometers arrayed below, and this is all experimental, right? This is not computational. This is all experimental. And so we can see the flow, which we're going to visualize with Schlieren. So we're going to be able to see shock waves, and we can see the pressure through the system, which we are going to visualize using these manometers.
See what is happening in the channel by using a Schlieren optical system to make
Let's let it
density
buffer.
variations visible. The mild boiling motion is turbulence in the room outside the channel.
Okay, so now what's happening is we're decreasing the back pressure, right? So just like we talked about in class, we're decreasing the back pressure. We're still at the point where the flow is subsonic everywhere. Okay, so we see the pressure is decreasing as the flow speeds up, and then recovering again on the other side. Okay, so this is still subsonic flow everywhere at this point.
Now, watch the throat. As the noise.
So we reached a point where we kind of got to like a minimum pressure here, right, at the throat, where we were transitioning from everywhere. So at this point, we still have subsonic flow everywhere. So this is like, if we go back to our slides on this, when we're talking about flow through a converging diverging nozzle, this is like this condition C. Remember, we showed a curve C where the flow is just about sonic at the throat, but is everywhere still subsonic. That's exactly what we're seeing right now in this flow. And now we're going to look at the case where the flow trips to supersonic, and we're going to see what happens to this pressure distribution.
As the noise changes, a shock wave appears at the throat and moves.
So now we're at this case where the flow has now, we've lowered the back pressure enough that the flow is now becoming supersonic on the downstream side of the throat. So now we're in one of these cases here, right? But you'll notice that we still have pressure recovery to match what that back pressure is, with an abrupt discontinuity in pressure, which we can actually visualize when we get back to that. And so now we're on something like curve D, and we're going to keep decreasing pressure until we get to eventually to something like that curve H, which we talked about last time, right? So we can start to see that there's, we can kind of make out a discontinuity here in pressure in these manometers, and that corresponds to the location of the shock wave, which you can visualize in Schlieren.
Into the diverging part of the channel. The position of the shock wave matches the discontinuity in pressure.
So we're
Here's a
watching.
close-up of the shock wave form. The appearance of a shock wave in the channel means that the flow is locally supersonic.
So now, for example, we know, and I asked this question last time when we were live, so I won't ask it again, but we know that the Mach number here is equal to Mach number 1, right? Is equal to 1, because we can see that we know that we have subsonic flow upstream. That's where we were coming from stagnation, and we know that we have a shock wave here. It's a normal shock. We know the flow upstream is supersonic, and therefore the flow must have been Mach number 1 at this point. And now we can see as
The
we,
difference between this symmetrical flow and this unsymmetrical one is that now the velocity is sonic at the throat. This transition to sonic flow at the throat with all of its consequences is called choking.
okay, so this was talking now about choke flow. But actually in this example, we never actually got to this case of condition H. But we're going to look at a little bit more complicated setup where now we're going to have
The second throat, a
second throat that they can actually adjust. The experimenter can actually adjust. In that case, and I'm going to reload this while we're waiting. And so now in this experiment, we're going to see that they're actually able to adjust the effective back pressure felt by that first throat and actually reach that condition.
the second throat a little more,
They're going to be able to reach something like that condition H in this channel.
so that it will not choke even for the strongest possible shock wave at the test section Mach number of 2.3. The first throat has choked, but the second has not. The back pressure is still decreasing, and the shock wave is moving downstream in the channel. Suddenly,
So here we can see that this is very analogous to what we were looking at in the previous video, at least for this first throat, where the Mach number is 1 at the throat. We know it's subsonic upstream. We know it's supersonic downstream because there's formation of shock waves. And so, and we can see now that that shock downstream is trapped right within here. We've been saying, so the flow here, even though there's another throat here, this flow at this other throat is not choked. And so the Mach number here is not 1. In this current setup, the flow never accelerates to the point where it achieves Mach number 1 at this second throat, right? So we go from subsonic, sonic at the throat, supersonic right here. We cross the normal shock wave, we become subsonic again. We accelerate as the nozzle area decreases. But we don't accelerate to the point where it becomes sonic in this case. And now we're going to see, as we're going to continue decreasing the back pressure, we're going to look at what happens to the shock wave within this channel.
the shock wave jumps into the subsonic.
So now we can see that the shock wave has completely cleared. So this is analogous to that like condition H, where the shock has now moved entirely out of the system. And we can now see, that here. And another feature that I want to note here are these little waves here. These are little disturbances, little tiny Mach waves that are caused by disturbances or roughness on the sidewalls of the channel. From the angle of this, and you'll see this in the homework, this is what I'm asking you to do in one of the homework problems, we can estimate what the Mach number is locally at each section of this channel. All right, last thing is for external flow.
We're losing our vacuum.
So this is
Hey, we're losing
destined
our
for
vacuum.
Smarter Every Day.
Do you want to shoot? Here we go. You ready?
So they created an air cannon to launch a baseball. I do not think this would be a good capstone project. It's a little bit maybe too dangerous for what we would typically want to do, but it's pretty cool to watch.
Ready? 3,
Okay, hold on. My
2,
other son wants to watch this.
1. What on earth? Where'd it go?
That ball disintegrated.
No, it didn't.
I think it hit the.
It did hit the back. It did. Oh, get the tank is safe.
Shred it, man.
Oh,
Oh, wait, you can see the seams.
that's fantastic. Okay, so at some point we're gonna get that high speed. Oh man.
I love his
Okay, cool.
enthusiasm.
Let's go do science.
So
I
that's
don't
also
think that one's gonna be supersonic.
Okay, here we go. Moment of truth. I gotta admit, when I first saw this, it was genuinely hard to believe my eyes.
Okay, so now he's visualizing the flow around this baseball with the high-speed Schlieren setup that he's built. And so again, we're going to see density differences in here. And he's basically looking for a shock wave, right, as indication that the baseball was moving faster than the speed of sound.
There it is. And there's a lot
Okay,
going
yeah,
on
so-
here.
Oh, wait.
Oh, man. You got,
Dude, what have we done? Look at it. It's beautiful.
can we just walk over and put a ruler in front of?
That's
the arrow
supersonic.
And then we'll know how much that transient space is.
You can tell it's supersonic by the angle. Like it has a Mach cone.
There's another,
All right, and we're gonna have to call it there, and I'm gonna have to let you go. But he says it's supersonic. You can tell because of the angle and the Mach cone. And he actually goes in and does a calculation of what that angle is to figure out that this baseball is moving at over 1,000 miles an hour. All right, class. Thanks very much for bearing with me today. I'll see you all on Monday. I'll send an email more than 40 minutes before class about what format we're going to use. And we're going to talk about aerodynamics and flight. All right. Thank you all. Hope you have a great weekend.